that guy told a great story. You just gave me almost a monosyllabic run, which was correct, but give me a story. So explain it using,
Well, salmon eat full of bacteria.
well, just, once this, we'll let the salmon get up the stream first. So how do they go from, being in the stream trying to spawn to suddenly?
They're just, get some, then eat some, or stuff like that.
Alright.
Just around. They also crop out the salmon remains.
Now your story's getting complicated because now there's two timelines. We've got bear crap containing salmon, and we've got salmon carcass. So make a decision, go one way there.
I'm gonna go with the salmon carcass.
Alright. So we've got a dead carcass in the ground, and what's happening?
Okay. Guess it is where it's
Then what decomposes the nitrogen from it, the salmon goes into the soil.
Using, what's our flux word?
mineralization.
Alright, okay. So as that salmon is being decomposed by our friends the decomposers, that nitrogen is undergoing mineralization and entering the soil. Alright, good job. Right. So we've got nitrogen probably in the form of ammonia in the soil via decomposition. So now how does it get from the soil into the vegetation? Oh, you're volunteering the next person.
Once it's in the soil because of mineralization, the plants then multiply into their own.
How does a plant, does it say like nitrogen atom immobilized immediately?
It absorbs it through its roots.
Okay, so it's taken up through the roots. Yep. And it moves into the roots when it's dissolved in water. So it's not like it just grabs an element. It's in solution. And so when the plant's uptaking water, the nitrogen's moving along with that water into the roots. And then magic plant biochemistry, it gets converted into something useful like particle, a very, very small particle. All right. So with our salmon and our bears, we had basically a process in which we could see how mineralization followed by immobilization would take place to move that salmon from the creek with the help of the bear into the soil and then ultimately up into the tree. Right. Second question. In thinking about the amount of nitrogen in the trees that comes from the salmon, would you sort of imagine that this is sort of, sure, we've got a crazy guy walking through the woods looking at that salmon. Is he sort of exaggerating how important this is? Like, are these trees like made up of like all nitrogen from marine-derived salmon, or is it like 2%, but he's just sort of telling a story to try to get the sort of the gist of the interconnectedness of the world? What do you think?
I would say a story seemed a little bit fishy, one could say. I would say to start out, yes, the fish are important, but there are other ways nutrients could be transcribed, such as from the trees themselves. As the trees fall down, they decompose, become mineralized into the soil. And I think there are many other processes going on. He's just working out one involving a fish.
It's just looking at one. Different view, or?
It would depend on how many nitrogen-fixing bacteria are present. If there are very little or none, then yes, it's probably a very important source of nitrogen in the environment. Granted, I don't know enough about Alaska forests to be able to, actually make a comment on how important this is, but it would depend on how many nitrogen-fixing bacteria, mostly.
I'm gonna go with that actually is pretty important, because Alaska, it's pretty harsh there most of the time and not much survives. When they do get new nitrogen sources in there, even if it's seasonal, it's gonna be a huge boost to the ecosystem while it's there and kind of adjust in the meantime.
So your team salmon, your team trivial.
That counters the point.
No, you can't counter his point. We'll get to the truth eventually. Yeah, it's always a fight. It's science, right? For not just yes.
I think that even though I do think that there are other forms of, there are other mechanisms because I agree that like Alaska is one of those places that's not, to me at least, from the outside looking in, super stable in terms of their access to different types of animals and things like that. So I imagine that anything that does exist there is specialized to them.
So we have 2 team salmons, we have 1 team trivial. Does anyone want to jump on team trivial to even things out? Another case against the importance of salmon.
Nature is never just one process going on, or at least I don't have any examples of it just being one singular process. It's not going to be just, oh, the salmon are the entire driving force of this ecosystem. For instance, like, if I had to add one extra process that might bring in nitrogen from abroad, I'd say probably migratory birds coming into the area.
Alright. Now, one of the fun things we can do as scientists is we've actually figured out how to tell the difference between nitrogen that comes from marine sources and nitrogen that comes from terrestrial sources. Now, and we're not even talking about different forms of nitrogen. We're actually talking about elemental nitrogen. And the beauty of it is the ratios of marine nitrogen tend to have a little bit more stable isotope, which we like to call delta N15, or nitrogen 15, than terrestrial sources do. And there's all sorts of esoteric reasons why that is. But marine-derived nitrogen is just going to have a slightly higher ratio of that nitrogen 15 isotope than the standard nitrogen 14. So we can use, if we can basically fractionate out the nitrogen and look at the ratio of common nitrogen to your isotopic nitrogen, we can actually figure out whether or not that nitrogen is largely from terrestrial or from marine sources. So we can use that as a proxy to get at this question of how much of that is actually coming from the salmon versus how much is coming from terrestrial sources.
So my answer, we can't know what current information is. Because we weren't given enough information.
You were not given enough information. I'm giving you more information.
Nice, okay.
All right, so all I'm saying is we have a yardstick now that we can actually measure that nitrogen. So we don't have to speculate. All right. So in order to figure out if we get a little or a lot of our nitrogen from salmon, we can read this abstract. And again, we've read abstracts before. Go through once, figure out what terms we need to define in order to make sense of this. But there's going to be some terms in here that you know and recognize. What words do we need to define? Anadromous. Yes. Very first word. Hopefully that didn't stop you from getting to the second word. All right. What this refers to is a fish that spends part of its life in freshwater and part of its life in saltwater. So these Pacific salmon are actually born in freshwater streams. They go downstream, spend their life in the ocean, get big, and then come back up that stream. spawning. So it just means they're living in two worlds, freshwater world and saltwater. Yes?
Riparian forests.
I'm sorry, could you say that again?
Sorry, I'm far back. It looks like you're saying riparian forests.
Ah, riparian forests, right? So I don't have to define forest for you, we're good there, right? Just that modifier. Riparian refers to a forest that grows along a stream or a river. Kind of where you might find some sap. Any other words? This is what I do professionally all day when I'm doing my own abstracts and reading in areas I'm unfamiliar with. Step one, figure out the words you don't know, right? Get a handle on it. Then once you figure out what's going on, give it a second read, okay, and see what starts to make sense. And that's sort of the key to help you get into any literature that's sort of really alien to you or initially difficult. Find your terms first. It's a little bit easier on the second read once you get those terms nailed down. All right, so back to our question of how much nitrogen is actually coming from the salmon. Is it a little bit or a lot?
A little less than a quarter.
A little less than a quarter. All right, so that's quantitatively correct, but we call that a little bit or a lot?
That's
Oh,
the
it is a lot.
species providing a quarter of the nitrogen,
It's quite a bit.
at least in the foliage.
Yeah, so in terms of our sense of things, you know, the sort of our qualitative description, it seems like a lot, that one species is sort of responsible for a quarter of the nitrogen that has been immobilized in these citrus fruit trees, which is really kind of cool. So the crazy guy walking through the forest, you know, he probably knew this, which is why he was just so excited about finding all these dead salmon, because he knew the story, right? And not just in a broad general sense of things, like, oh, you know, everything's interconnected, isn't that wonderful? But no, the salmon's actually a major contributor to those forests. Right? So we read the abstract, so it's basically like the trailer for the paper. You got sort of all the highlights. But you know, as scientists, we often need to dig into the evidence that sort of supports the claims that we read initially. So here we've got a nice thick data table, and there's a lot going on. So in terms of trying to break down information that we encounter in data tables, how do we do that? First thing we want to do is we want to read the legend. Skip all the numbers, skip all the bits, read the legend. What does the legend say? Read it for us. I'll give you a hint. Delta, B delta 15. All right, excellent. All right, so what have we got here? We've got our delta nitrogen 15, so that isotope, as opposed to your standard run-of-the-mill normal nitrogen 14. So we've got information about our nitrogen isotopes. We have information about our carbon to nitrogen ratios. I know it was like all the way back last Tuesday, but that's another term that we've seen before. And I sort of indicated that that's sort of an important indicator. Sort of in the foliage of riparian vegetation. So there's that riparian word. Thank you for bringing that along. And then we're looking at spawning and reference sites. Okay, so this study was looking at sites with salmon. Okay, those are sites that are labeled as spawning because it's the fish coming up and reproducing or spawning in those streams. And then because we need some sort of experimental control, we're going to look at those compared to streams that do not have salmon spawning. And there's, you know, all kinds of reasons why a stream might not have salmon spawning in them. it's usually not like this year was just a bad year for that stream. Streams are either salmon streams or they're not, because salmon keep coming back to the same stream year after year after year. I mean, literally, you know, if they reproduced in water this deep in a tiny stream, they're coming back to that same spot at that same shallow level. Salmon are crazy like that. All right, so we've got our treatment stream, our salmon streams and our reference streams, or our streams minus salmon. All right, so great, we've got those three things. Next thing we want to do is sort of identify the variables in the table. We've already figured out the reference stream versus the spawning stream. So we've got data on the reference versus the spawning, reference versus the spawning. All right. Remind me, what's that carbon to nitrogen ratio all about? We saw that in the context of decomposition. What does that tell us?
Lower carbon to nitrogen ratio will decompose.
Okay, so the lower the ratio, it's going to decompose more quickly. That's what we learned last week. Another way of thinking about that is that for organisms, that lower carbon to nitrogen ratio is going to be a much more nutritious food source. It's going to be easier to digest. It's going to be one of those food items that's taken more quickly. And then, sort of our last thing is we look at our delta 15 nitrogen. I'm going to walk you through this because initially, if you look at this, this should make no sense to you, you know, unless you're an EES major, in which case, if you encounter stable isotope chemistry, it might make a little sense, right? But I'm guessing for most of you, it makes no sense. How can the concentration of nitrogen be negative? How can it be less than 0? No, that's not right. So when people report data on nitrogen or carbon isotopes, the way these values are calculated is they calculate the ratio of the isotope to a standard divided through by the standard. And so you end up with something that's going to be less than or more than the standard. So the negative value doesn't actually indicate negative nitrogen present in the sample. It indicates less delta 15 nitrogen than in the standard sample. Okay, so you can still interpret it as negative would be less, positive would be more, and not worry so much about, you know, what does the negative mean? All right. And then the last thing we have is we have our 4 species. We have Sitka spruce, which was mentioned in the abstract. We have Devil's Club, which sounds horrific, but it's actually not a weapon at all. It is a shrub. It does have some big thorns on it, hence the name Devil's Club. We have ferns of 2 different species, and then finally, red alder. Red alder, our special guest. Explain why that is. So that's what it is. All right, so with Sitka spruce, what does our data tell us about Sitka spruce in spawning versus non-spawning or sort of salmon-free streams? And so they're looking at the leaf chemistry, so they're looking at the foliage, the nitrogen content of the foliage in that Sitka spruce in areas next to streams with and next to streams without salmon. Yeah.
There's a significantly lower carbon to nitrogen ratio.
Okay. We're going from 39 to 32. We got a little asterisk here, which tells us a significant difference. All right, so what do you think that means? How do you interpret that?
So that would wrongly suggest that Sitka spruce in spawning sites would be more nutritious.
The leaves themselves would be more nutritious, yes. And in addition, which is not obviously or apparent, is it's going to indicate that the soil is going to be more nitrogen rich, which is why it is able to have so much nitrogen in its leaves relative to a place without that. So the soils are nitrogen enriched, and that's reflected in the leaves themselves. Mobilization, right? What else about Sitka spruce can we infer from the data table? Take us on, Doug. Take us to nitrogen.
It has a higher mean of the nitrogen 15 isotope weights.
Which means what?
Ratios of nitrogen in aquatic animals contain more stable isotope.
All right. So interpret it for me. So where's that nitrogen coming from?
It's coming from the fish. So
All right. So on our spawning streams, a greater fraction of the nitrogen in the foliage is of marine origin. All right. That's our interpretation. All right. Now, if we look down at Devil's Club and our two species of ferns, we see the same general trends. We see Devil's Club, higher carbon to nitrogen ratio in our reference streams versus our salmon streams. Significant. Same is true for ferns. 19.6 versus 16.8, significant. So a little bit smaller than we saw with Sitka spruce, but they're also taking up more nitrogen in these salmon streams. And then likewise, if we look at our ratio, of our delta 15 nitrogen ratios, in other words, how much of that is marine derived, we see that more is marine derived for the Devil's Club and then also for the fern. So these first three species all seem to be marching together. They're taking up more nitrogen of marine origin. There's more nitrogen in the environment, which we're inferring from this carbon to nitrogen ratio. And because as those needles fall and as those Devil's Club leaves fall and those fern leaves fall down to the forest floor, they're going to decompose rapidly because they're more nutritious, which is going to make that nitrogen re-available more quickly than in those reference groups. Okay, so nutrient cycling, in fact, in the soil, basically the process of mineralization and of nitrification and re-immobilization is going to be faster. So all really cool. But now, who comes along and ruins our perfectly good story about salmon? Red alder. Red alder. Alnus rubra. All right. Carbon to nitrogen ratio with a reference stream of 16.5 versus 16.6. You've got to be kidding me. It's the same. All right. Negative 1.04 versus negative 0.91. You're on the wrong side of the standard. They're not significantly different. Why would red alder come along and ruin our perfectly good story about how important salmon are in the overall nitrogen cycling in this forest? Yes?
Does that have something to do with it being a deciduous tree?
Does not have something to do with it being a deciduous tree, which is a good guess. Devil's Club is also deciduous. Oh, sorry to shoot you down, but it was an excellent attempt. Someone else want to make a go at red alder? Yeah. I like the way you're thinking. It's not entirely correct. There's nothing preventing it from taking up salmon-derived nitrogen, but you're on the right track. So,
Is it much like lagoons? Does it have a very close symbiotic relationship with the bacteria in the soil, which is already giving it a lot of nitrogen?
aha! Red alder is able to form these symbiotic relationships with nitrogen-fixing bacteria. So they're actually getting their nitrogen through the process of nitrogen fixation, particular flux. So in this case, red alder actually turns out to be a secret control that the researchers put in here, right? Like, okay, we're going to stick in a species of the nitrogen fixing, which really shouldn't rely on salmon-derived nitrogen, and let's see what this one's doing compared to everything else. And you know what it's doing? It's doing its own thing. Yeah, a little bit of that salmon-derived nitrogen is getting in, maybe. So, the last bit here, we'll get through this graph and then we'll call it a day. We wouldn't get phosphorus. So, last graph to work through. What is our, okay, so orienting graphs, we've done this before. What is our response variable on this graph? Basal area growth. What does basal area growth mean? Right. Basal area growth refers to how fat trees get. Right? So if something is growing 2,000 millimeters per year, that's basically putting on 200 centimeters of girth per year. Or I'm sorry, it's cubic millimeters. So not quite 200. Anyway, it's growing about 20 centimeters per year in terms of its overall rate. So it's getting to that. It's how quickly it's. What's our predictor variable here?
Spotting was reference sites.
Okay.
So whether or not it's the same as spotting.
Whether or not we have salmon sites or non-salmon sites, our reference sites. All right, we've got another wrinkle that we've sort of thrown into this graph. We've got the stripy bars and we've got the open bars, or we call them open bars, but the white bars. Scientists call them open bars. There's a whole reason for that. All right, so what do those bars represent?
How far away? Whether there was a patient within 25 meters of the stream or beyond.
Okay, so the salmon were what's within 25 or further? The trees, exactly. The trees that we're measuring the growth from. All right, so we've got our salmon streams versus our non-salmon streams. We've got growth rates, and then we've got within 25 meters of the stream versus more than 25 meters of the stream. Why would distance from the stream make a difference? By who? Bear, or the ravens, and the other things coming in and dragging. So the idea is that the salmon should be concentrated relatively close to the stream. As we get further away from the stream, we expect that salmon increase to be less. So what's the... We're rocking 2 minutes. Get your 2 minutes worth. All right. So we've got sort of three things going on. We've got the streams, we've got the growth rate, and then we've got within versus beyond 25 meters. So within 25 meters, we see what? Just that really strong signal of much higher growth rates of those Sitka spruce trees close to the streams, but only in the spawning sites. In fact, if you look at the reference sites, it's worse. Growing by streams, it's a terrible place to be if you're a Sitka spruce. Once you're out of that sort of nutrient-rich salmon zone, we see that the growth rates of those Sitka spruce trees tend to be roughly the same. So essentially these riparian forests, and more specifically within 25 meters of these forests, are creating these nitrogen hotspots, which is getting reflected in the vegetation. which is fundamentally changing the whole ecosystem. So again, organisms like our salmon, like our bears, are playing a critical role in the transformation of nitrogen through these fluxes as we go forward. So we'll pick up here on Thursday. We'll do